Please be advised, right at the very first second of this broadcast, that this is an AI-generated analysis.
Yes, strictly AI generated.
Right. So I want you to imagine just for a second that you are managing a high-end Michelin star restaurant.
Okay, I'm picturing it.
Now, handing a really talented chef a single simple recipe, well, that's highly effective if you just want them to produce one specific dish.
Right, like a perfect souffle or something.
Exactly. But if you want that same chef to continuously cook a complex five-course meal for hundreds of guests,
Without stopping.
right, without ever stopping to, blindly search the pantry for missing ingredients, you can't just hand them a taller stack of recipes. It doesn't work.
No, it would be total chaos in the kitchen.
Total chaos. You must meticulously organize the entire kitchen ecosystem. And, well, welcome to today's comprehensive analysis. Today, we're doing a detailed technical review of the book Agentic Coding with Claude Code by Eden Marco.
It's an incredibly important book right now.
Oh, absolutely. And our mission today is to provide a comprehensive chapter-by-chapter analysis for highly technical professionals. We really want to explore how you transition from basic ad hoc chat prompting to actually building scalable, context-aware, multi-agent automated workflows.
Yeah, and the transition you're describing with that kitchen analogy, I mean, it represents a massive paradigm shift in artificial intelligence development.
For sure.
The whole software engineering industry is rapidly moving away from just, basic prompt engineering, and they're moving toward context engineering.
Because the old way is breaking down, right?
Exactly. Relying solely on static prompts just causes modern, long-running AI agents to fail because as the software project grows in size, the AI's context window just fills up. It fills with irrelevant code snippets, previous conversation
With
history.
redundant instructions.
Right. And this phenomenon is known as context bloat.
Context bloat.
Yeah. And when context bloat occurs, the AI just completely loses track of its original goal. And, that results in severe hallucinations, heavily degraded model performance, and, frankly, exponentially higher API costs.
Because it's processing junk over and over.
Exactly. So to solve this structural problem, Claude Code employs 4 distinct context engineering strategies.
Okay, lay them out for us.
Sure. So the first strategy is writing context. This establishes persistent memory, so the agent doesn't just, start from zero during every single coding session.
Right. Makes sense.
The second strategy is intelligent retrieval. The third is compression.
Right.
And the fourth is isolation.
Okay, well, let's unpack those mechanics a bit. Intelligent retrieval seems particularly important because it dictates how the AI actually finds the information, right?
Yeah, it's huge.
Because instead of just blindly searching the entire hard drive.
And wasting a ton of valuable processing tokens.
Right. Intelligent retrieval dynamically discovers relevant files based strictly on the developer's current working directory.
Exactly. It's targeted.
And then compression steps in, I assume, to summarize those long files.
Right, to minimize token usage even further.
Got it. And finally, isolation, which involves spinning up entirely separate specialized subagents to handle specific tasks.
Without polluting the main session's context window.
So establishing that operational baseline, it requires constructing system prompts that find what the text calls the Goldilocks zone.
Ah, yes. The Goldilocks zone. What's fascinating here is how delicate that balance actually is.
Because if a developer rigidly hard codes highly specific rules into a system prompt,
It breaks.
right, the logic just inevitably breaks down the second the AI encounters a novel, unexpected situation.
Conversely, if you provide instructions that are too vague, well, that just leads to chaotic and inconsistent code generation.
So how do you hit the Goldilocks zone?
You achieve it by teaching core architectural principles to the AI rather than attempting to, predict and rule govern every possible edge case.
Interesting. Give me an example of that.
Well, instead of telling the AI exactly how to write a highly specific sorting algorithm, you instruct the AI on the required performance standards and the preferred programming languages.
Oh, I see.
This strategy ensures the agent maintains a consistent identity and operational boundary, but it remains adaptable to new code-based challenges.
So taking this theoretical concept of organizing our kitchen ecosystem, it translates directly into the physical file structure of a project.
It does. Which brings us directly to the core mechanics of how Claude Code actually observes a project and builds its memory hierarchy.
Right. And the backbone of this organizational system is it's a simple text file named claudi.-md.
Yep, Claude EMB.
And the text utilizes a Next.js web application called the Hookhub project to demonstrate this.
Right. Next.js being a very popular framework for building user interfaces.
Exactly. And the Hookhub project serves as this continuous reference point for moving developers away from unstructured coding practices. Now, I have to confess something here.
What's that?
I have absolutely been guilty of what is colloquially called vibe coding in the past.
Oh, vibe coding. We've all been there.
Right. Vibe coding is where you basically just paste an error message into an AI prompt and just, well, you just hope for the best.
Without providing any clear parameters.
Exactly. And it inevitably causes the context window to just explode with irrelevant data.
Because it's grasping at straws.
Right.
Hmm.
So by using the claude.e.md file, developers move towards strict, spec-driven design. It gives the AI a clear map of the project architecture right from the very beginning.
And the memory hierarchy in Claude Code is highly deliberate to support that exact spec-driven design. It operates on two distinct levels.
Okay, what's the first level?
First, there is auto-loaded memory. This is the critical baseline information contained in the claude.md file that the agent reads immediately upon starting.
Got it. And the second level?
Second, there is the lazy loading of nested memory files.
Lazy loading, meaning it doesn't load it until it has to.
Exactly. The AI only accesses secondary documents based on explicit developer instructions, and only when a specific task requires them.
Oh, that makes a lot of sense.
Furthermore, developers can implement custom/commands. Book calls them skills and lifecycle hooks.
Hooks like what?
Well, for example, a developer can configure a lifecycle hook to automatically execute a terminal command, say UVI run playSound.py, the moment a background processing task completes.
Oh, so it physically plays a sound to give instant feedback to the human operator.
Exactly.
Okay, wait, I need to push back on this a little bit. I want to challenge the practical efficiency of this approach.
Go for it.
If a human developer has to spend hours explicitly configuring all these nested memory files, all these lifecycle hooks, and, strict file permissions just so the AI doesn't break the code base, haven't we simply traded coding time for administration time? I mean, does this heavy micromanagement not completely defeat the central promise of an autonomous AI?
That's a fair question.
It just seems like the developer is merely being demoted to the role of a babysitter for an algorithm. Where is the actual time-saving efficiency?
I get that. And that is a highly common and valid concern among engineers adopting these systems. But here's the thing. Explicit permission and lazy loading are mandatory architectural constraints.
Mandatory why?
They exist to prevent context poisoning.
Context poisoning.
Yeah. True autonomy without strict boundaries inevitably leads to unpredictable code generation.
Yeah.
An AI agent cannot autonomously decide which 50 files are relevant to a specific front-end visual component without risking the accidental inclusion of, say, irrelevant back-end database logic.
Right. It doesn't know where to draw the line.
Exactly. And if back-end logic enters the front-end context window, it will deeply confuse the AI's output. It leads to broken code and hours of debugging.
Oh, I see. So the setup time is an investment.
Precisely. The administration time spent configuring the claude.md file is a one-time investment that prevents continuous, catastrophic failures during the entire development cycle.
Wow. Okay. That clarifies it. So once these internal project boundaries are securely established, the agent frequently needs to interact with external resources.
It does. And that external interaction requires a standardized bridge to the outside world.
Right. Which is the Model Context Protocol, commonly referred to as MCP.
MCP, yes.
Now, the way I like to think about MCP is, well, it's like the universal USB-C standard for artificial intelligence tools.
Oh, I like that analogy.
Because think about it. Before USB-C, you needed a custom, tangled, proprietary charging cable for every single electronic device you owned.
It was a nightmare.
It was. And before MCP, developers had to write custom, tangled API connections for every single application they wanted the AI to talk to, whether that was Slack or Gmail or a relational database.
Exactly. It didn't scale.
Right. But with this new protocol, you build an MCP server once, and then you can plug that standardized server into any compatible AI client.
And the text outlines how MCP extends Claude Code to solve this massive industry-wide integration and portability challenge.
So how does the architecture actually work under the hood?
Well, the protocol achieves this portability by separating the architecture into three distinct components: hosts, clients, and servers.
Okay, break those down for me.
Sure. The host is the primary application running the system, like the Claude Code interface itself.
Okay.
The client is the internal networking mechanism that manages the two-way connection. And finally, The server is the component that actually exposes the external tools and data to the AI.
And the text provides some highly practical examples of this, right?
Oh yeah, integrating the Playwright MCP server is a perfect illustration.
Playwright, which is a framework for web testing.
Exactly. By connecting it via MCP, the developer grants the agent the ability to autonomously open a web browser, navigate to a local web page, and physically test the user interface buttons it just programmed.
That is wild. It's literally clicking the buttons.
Yeah. Another example from the text is querying LangGraph, which is a routing engine for AI workflows. By connecting to the Context 7 MCP server, the agent can retrieve external workflow states to understand what other systems are currently doing.
That's incredibly powerful. But, deploying these MCP servers has to introduce some significant operational risk related to context engineering,
It definitely does.
because the danger lies in overly general MCP configurations.
Right?
If an MCP server exposes an excessive number of tools to the AI simultaneously,
It severely pollutes the context window again.
exactly, the AI becomes paralyzed by choice. It wastes processing power and token limits, evaluating totally irrelevant capabilities.
Yeah, if we connect this to the bigger picture,
Yeah.
if the AI is tasked with updating a text color, it shouldn't have simultaneous access to database deletion tools.
No, absolutely not. That sounds terrifying.
It is. So the architectural solution to this danger is to scope MCP configurations strictly at the project level. By limiting the tools available to only those necessary for the immediate environment, the developer preserves the agent's focus.
Okay, so having successfully connected external tools via these USB-like protocols and secured the context window against bloat, the logical next step is automating the work executed through those connections.
Right. Moving from exploratory manual coding to structured parallel execution. That's where agentic workflows generate the most substantial business value.
And the text details how integrating the GitHub platform into Claude Code allows for the total automation of pull requests and issue resolution.
Yeah, the AI can read a bug ticket, write the code to fix it, and submit the solution for review autonomously.
But before any code is modified, the system has to utilize a safeguard. And the book calls this planning mode,
Planning mode.
which is a brilliant mechanical safeguard. It restricts Claude Code strictly to read-only operations.
Which is crucial.
Right. During this critical phase, the AI is physically incapable of changing a single line of code. Instead, the agent analyzes the code base and generates a formal written specification of what it intends to do.
And only after the human developer approves this written specification does the agent actually transition to modifying files.
Okay, here's where it gets really interesting. Once this planning phase is complete, the concept of parallel execution is introduced.
Right.
Parallel execution involves running multiple AI agents simultaneously to accelerate development workflows, but this introduces a massive mechanical vulnerability.
It really does.
If we unleash multiple autonomous AI instances in parallel on the exact same code base, how do we prevent them from stepping on each other's toes and creating, catastrophic merge conflicts?
And that is precisely the architectural flaw inherent in early parallelization attempts. Running multiple AI agents with shared file access is inherently fragile.
Because they're tripping over each other.
Exactly. If Agent A is tasked with modifying a core utility file, while Agent B simultaneously attempts to import functions from that exact same file,
Boom.
the entire software build will fail. The system will collapse under its own conflicting changes.
So what's the fix?
This vulnerability dictates why developers must move toward formal branch isolation and deploy specialized subagents.
Sub-agents, okay.
Yeah, because shared file parallelization is far too risky for production environments. The architecture must evolve to isolate execution contexts securely.
So achieving this secure context isolation requires understanding the exact mechanics of a subagent. A subagent is basically a secondary AI instance that runs in its entirely own isolated context window.
Right. Which prevents the main session from becoming polluted with all the messy intermediate reasoning steps of a complex task.
And the text introduces the infinite agentic loop pattern to explain this.
Yes, the infinite agentic loop.
In this loop, a subagent generates code, automatically runs a test, reads the resulting error message, and rewrites the code. And it iterates this cycle independently until the tests pass.
Without bothering the main agent at all.
Exactly. And to activate deeper reasoning within these subagents, developers utilize the Think Deeply directive.
Which forces the model to spend more tokens on reasoning before acting.
Right. Additionally, variables like arguments are used to manage data passing.
The arguments variable is so important.
It acts as a secure data pipeline, right? Moving specific instructions from the main agent to the subagent.
Exactly. And these encapsulated workflows, powered by those data pipelines, are often defined as agent skills.
Hmm.
The behavior of these skills and subagents is heavily shaped by output styles.
Output styles, like what?
Well, enforcing structured YAML responses, for instance, is a critical technique.
YAML being a data serialization language.
Right. By forcing the AI to output its final answer in strict YAML formatting, the developer guarantees that the output could be parsed programmatically by downstream software systems without any human translation.
Oh, that makes sense.
The text further describes the concept of role-based contexts. In this configuration, multiple Claude Code instances are structured to mimic a specialized startup team.
Mimic a startup team.
Yeah, you configure the system prompts so that one AI instance acts exclusively as a user interface designer. Another acts as a DevOps engineer handling server deployment. And a third acts as a database administrator optimizing queries.
Wow. This shift is highly analogous to the structure of modern medicine.
How so?
Well, instead of relying on a single, overwhelmed general practitioner to diagnose every possible ailment and perform every surgery,
Which never works.
right, you coordinate a hospital full of highly focused specialists. Each specialist only receives the medical charts relevant to their specific domain.
That's a great way to put it.
And in our software scenario, the arguments variable is the exact mechanism used to securely hand the relevant medical charts from one specialist to the next.
Exactly. But coordinating a hospital full of specialists requires a robust administrative infrastructure.
It certainly does.
Which brings us to how these AI agents are managed and orchestrated across local and cloud environments. Orchestrating parallel development seamlessly across these varying environments relies heavily on the integration of Claude Code within both desktop and mobile applications.
Okay, so how does it manage the files without conflicting?
The pivotal technical concept enabling this orchestration is the use of Git work trees.
Git work trees.
Yes. Traditionally, switching between tasks in version control requires stashing your current files to load new ones. Git work trees solve this by allowing multiple branches to remain active simultaneously in entirely independent physical directories on the hard drive.
Oh, so they're completely separated on the disk.
Right. For example, the text uses the specific feature branches, Vigilant Feistel and Zealous Jemison. By checking these branches out into separate physical folders, multiple AI agents can perform independent feature development concurrently.
So Agent A operates strictly in folder A, while Agent B operates strictly in folder B.
Eliminating the risk of conflicting file modifications completely.
Okay, but while the concept of Git work trees is powerful, I must again challenge the practical efficiency for the human operator here.
Okay, let's hear it.
If a human developer is required to actively monitor 4 different Git work trees, while simultaneously reviewing and merging outputs from 4 different cloud and local AI agents, well, does the coordination cost actually exceed the time saved by parallelization?
That's the trap many teams fall into.
Right. Are we overwhelming the human reviewer with too much simultaneous output?
The text provides a crucial rule to address that exact administrative inefficiency. Parallel agents only yield a net positive return on investment when the assigned tasks are strictly independent and well-scoped.
Strictly independent.
Yes. If the tasks are exploratory, or if the features highly overlap in the code base, parallelization multiplies uncertainty rather than productivity.
So it actually slows you down.
It does. In those overlapping scenarios, the human coordination cost will absolutely exceed the development speed, negating the benefits of the AI entirely.
Wow.
This strict discipline around formal planning, context isolation, and measured orchestration ultimately defines the highest tier of AI systems operating in production today.
And that distinction really brings us to the architectural taxonomy of these systems. The text concludes by defining what actually constitutes a deep agent.
Right. It differentiates between shallow agents and deep agents.
So shallow agents fail under the pressure of context bloat because they rely on simple, rigid loops.
Exactly. They just spin their wheels.
Yeah.
Deep agents, however, are engineered for long-horizon, highly complex tasks.
Right. And frameworks like the LangChain Deep Agents Harness and Claude Code itself are built upon 3 foundational pillars.
What are the 3 pillars?
First, they require a formal planning tool, functioning as dynamic, updating to-do lists. Second, they require hierarchical delegation.
Meaning the ability to utilize the specialized subagents we discussed.
Exactly. And third, and perhaps most importantly, They require direct file system access.
Yes.
But why is file system access the ultimate defining pillar of a deep agent?
The file system is critical because it fundamentally changes how the AI maintains its orientation. In this new paradigm, the file system is no longer just a static repository for holding code. It actually acts as the AI's persistent state and its precise context selection mechanism.
Oh, I see.
It is the engine that allows the deep agent to pause its work, reflect on the current directory structure, and resume complex tasks days later without losing its train of thought.
That is incredible.
And to govern this deep execution, system prompts must scale accordingly. System prompts for deep agents span hundreds of lines.
Hundreds.
Yes. They are carefully engineered to build a complete cognitive baseline for the AI's identity, define its operational boundaries, and establish strict error handling protocols.
So it's not just a prompt anymore.
No, it represents a fundamental shift in software engineering. The discipline is rapidly moving away from writing functional syntax and moving toward managing complex cognitive systems.
Which leaves us with a final provocative thought to consider today.
Let's hear it.
If the file system is actively serving as the AI's persistent memory, and some agents are successfully fulfilling the specialized roles of an entire software engineering team passing data pipelines between them, what will the integrated development environment of the future actually look like?
That's a profound question.
Will human developers even look at individual lines of code in the years to come? Or will you exclusively review high-level agent architectures, YAML output styles, and massive system prompts?
We must remember that we are no longer just handing a chef a recipe. We are designing the architectural parameters of the kitchen itself.
Exactly. To master the design of these advanced systems and prepare for that future, we strongly and formally recommend that you read the actual book, Agentic Coding with Claude Code.
I couldn't agree more. The practical examples and the underlying technical architecture detailed within its pages are absolutely essential for any technical professional navigating this industry-wide transition.
Friends of the show, we actively encourage you to subscribe to this broadcast for future comprehensive analyses of emerging technical systems. We wish you a great day.